Okay. And also another fellow is Sandra. Is that also from Padidi Research Group?
Yes.
Okay, good. Okay, yeah. Welcome. Okay.
Yeah.
All right. Okay, I think let me see. Okay, I think we just have to follow the schedule, and maybe by the time I start, people keep joining this section. So let me see. Okay, so maybe I still didn't see Professor Katie Wong join. So then let me start by give introduction of about this webinar. Okay. Okay, so Alex, can you see my full screen mode?
Yes, can see, Professor.
Okay, good. Okay, all right. And let me resize it. Sorry. Okay, welcome everyone to join this quantum forum, the quantum science and computing online forum. This is Dr. Kalok NG. Okay. So this is a forum which is co-organized by me and Professor Huang, KT Huang, and Alex Sun. At the moment, Professor KT Huang hasn't joined this beginning, so maybe he will join this sometime later. All right. So the aim of this forum is to provide a platform for learning the basics and the latest development of quantum science and computing. A cutting-edge field that explores the power of and potential of quantum physics for computation and information processing. We hope this forum is able to inspire and motivate you to pursue your curiosity and passion for quantum science and computing, and to equip you with the necessary skills and the knowledge to understand and apply quantum science and computing concepts and techniques. Now, we have a website edited. This is the link quantum.asia.university.w. So when you follow this link, then you double click this icon, then this will carry you to another web page. So if you have not signed up before, so please use this link to sign up. So this will, if you click on the sign up, this is the sign up page. So you just have to sign up once. You no need to do it again. Your record will be kept in our database. And another thing is we are welcome for those who sign up to volunteer to give presentation. So if you are interested in to give an online presentation, so please fill up this form and send it to me, okay, to this address. So we will make the arrangement for you, right? So now, subject to the speaker approval, we will send you the lecture notes and the link of the video recording, usually within 5 days after the presentation. So I have a co-work with Dr. Human Padidi to organize a series of upcoming 5 events. Okay, and this is the first one, and the first one is today, March 15. I have already allocated the next 4 events is scheduled on every Friday afternoon, 2 p.m. at Taiwan. But I assume all the presenter is able to make it, but in case it is not, we have to reschedule, then I will inform you as soon as possible. But so you can look up this table and then reserve your time to join us in the future. Okay, so this is a series of events on quantum machine learning and its biomedical and physical applications, right? So today there will be me for giving the first presentation, and Mrs. Aninda Astuti. Okay, she will give the demonstration right after my talk, right? So, so here is my resume. Okay, my introduction. I earned my PhD degree in physics at Vanderbilt University, and I'm a distinguished professor in the Department of Bioinformatics and Medical Engineering at Asia University in Taiwan. I've already published more than 100 articles in the scientific journals and conferences. With the article covered topics such as next generation sequencing, multiomics, computational system biology, network biology, DNA data hiding, high energy physics, and polarization of cosmic microwave background radiation, which is a topic in cosmology. So my current research is doing something on using open quantum system approach to study DNA quantum biology and the use of quantum machine learning tool to identify cancer biomarker and network isomorphic problem, right? So for that, so let me switch to another PowerPoint. Okay, yes, this one. All right. The overview of quantum computing. So Aninda, can you still see my desktop?
Yes, Prof.
Okay, all right. So today, this is the title, Overview of Quantum Computing and Qiskit Demo, a collaboration with my PhD student, Aninda, right? Okay, this is the content of my talk. The first part is about quantum phenomenon, the spin, discretization of spin and wave particle duality. And then I will highlight some of the major concepts of quantum mechanics and quantum computing. And then move on and talk about the quantum bit and how you represent a quantum bit using the block sphere picture. And then say about the gate and the universal gate set and the measurement basis and entanglement. Then I will also talk about the Deutsch algorithm and also about the pros and cons of quantum computing. Then after I finish this part, then I will pass my microphone to Aninda for the IBM Qiskit demo. Okay, now it's more than 100 years ago, this Stern-Gerlach experiment leads to the discovery of the spin quantization of electron. So what these two gentlemen are doing is they send the silver, highly heat silver ion from this position 1. And then because of the high temperature, then the electron get ionized. And when they pass through this magnet, because of the spin direction, okay, you can think about this is like the interaction between the two magnets. Then the electron will hit on this screen. Now, if in the classical picture, a spin object can spin in any direction. So you expect you will see a bang a band, okay, a line of the electrons hitting on this screen. It turns out the experiment only see 2 spots, this one and this one. So this is in contradiction with our classical picture of a spinning object. So people realize that the spin is quantized. So there's only 2 possible states, spin up and spin down. And we use a quantum number 1/2 to represent 2 possible. So because of the 2 times of s plus 1 is equal to 2. Right. Now another experiment just 1 year after this one is the double slit experiment. So on the left-hand side, you send a bunch of electrons through 2 slits, and then at the right-hand side, then you have the detector for the detection of the electrons. And in the classical picture, you expect if you treat the electron as a particle, then you expect you only see 2 lines at the back. But in fact, you see there's a wave pattern. Some pattern, some of the region you see, you also see the electron hitting the screen. So this can only be understood in terms of the wave picture, if you, but not in terms of the particle picture. So that means in the microscopic view, you have the wave and particle interpretation at the microscopic view, right? So this is the so-called wave particle duality. That is before you doing experiment, that the particle is, you don't know whether it will behave as a wave or particle. Some experiment you have to explain this by a particle picture. For other experiment, you have to explain this by a wave picture. Sorry. And then this is a very famous picture back in 1927, where we have a lot of people, they make important contribution in quantum mechanics. So one of the famous one is the Schrodinger, who is standing over here. Okay, now to move on from quantum mechanics to classical mechanics, what you have to realize is we have to describe the status of using the quantum state. Now we have if we consider something called the physical observable, there's something which is experimentally measurable. And this is a list of the observable, like position, momentum, energy, angular momentum. So to translate from the classical description to the quantum description, what you have to do is you replace the classical symbol, like the position, momentum, energy, in terms of something we call the operator. And you can represent the operator by, say, the derivative, taking the derivative of with respect to the coordinate and stuff like this. So now this operator has a certain properties, which is the so-called Hermitian. Hermitian, that means if you represent the operator by a matrix, then the eigenvalue of the physical observable operator are real number, because all the measurement are real number. All the physical observable are real number. Like the energy is a number. It cannot be have a complex component. Okay, and the state is described by a vector in the so-called Hilbert space, where the inner product of the vector is defined. Now, if you want to learn about quantum computing, then you have to get used to the so-called direct bracket notation. So bar means you write the quantum state with a symbol like this. And if you put a dagger over here, that means you're taking the complex conjugate. So you have to get used to this notation. Okay, now it's before I talk about quantum computing, let me say something about the quantum technology. Quantum computing is only a part of the quantum technology, and we also have a lot of development in something called a quantum network, or the so-called quantum communication, in which you send out a quantum particle between say people at position A and B, and also about quantum sensing. That is, you can measure something like, say, temperature or resistance with a very high precision with the help of quantum science. Now, in this series of lecture, we will only focus on quantum computing. And some scientists believe that the universe is a giant computer. This is an idea put forward by Seth Lloyd, who is a professor at MIT, and he wrote a book named with the title "Programming the Universe." Okay, so a lot of the country they try to pursue faster computing speed and hope to apply this in military and commercial and other purpose. And if they can achieve, then it's expected that it will become a superpower. Okay, now the origin of the quantum computing is you can trace it back to 1980. Okay, by this two fellow. Okay, Yuri Mani and Paul Binoroff. Is even before Richard Feynman. Some people say Richard Feynman, who is put forward this idea, but he's not the first one. But of course, he's a very famous physicist who won a Nobel Prize for the development of quantum electrodynamics. Now, there are four classes of a problem. So on this XY axis, I put the classical on the left and classical on the bottom. So quantum computing is we trying to stimulate the quantum state. The classical state stimulated by quantum state. Now, in the traditional approaches, the CC. That is, we use the classical state. That means using the compute the classical logical bits to simulate your data, just like what we are doing in machine learning and deep learning. But in quantum computing, we are using we encode the classical state by the quantum state. So that is the difference. Now, there are at least two models of quantum computation. Now, the one that you most often see is the gate or the circuit-based quantum computing. That is, you do all the computation with the help of a quantum circuit. And the circuit is made up of the quantum gate. It's because it's we have a lot of knowledge in the classical Boolean algebra, the logical gate. So it is more easy to understand the computation in terms of the circuit-based model. Now, the D-Wave is a Canada company who developed the so-called quantum annealing approach for doing quantum computing. There is, due to the quantum tunneling effect in quantum mechanics, they try to search the minimum ground state for the ground state is correspond to our solution. And another one is the adiabatic quantum computing, in which you prepare an initial Hamiltonian, and then you and then you slowly change the system to the final state, so that the final state is will give you the solution for your problem. Now, some people say quantum annealing is not a universal quantum computer. So they can only deal with the optimization problem. So as I said, the gate-based quantum computation is based on free idea is we can do a quantum because of the parallelism. And then about the you encode your a state with a qubit, and then you use a series of quantum gates for doing the manipulation operation, and then because of the interference among the qubits, then hopefully you design your algorithm in such a way that the solution will come out as has the highest probability. That is, your measurement will single out. Right. I don't know too much about the measurement base, but this is another approach model for quantum computing. But hopefully, I will learn this later and give a presentation in this webinar. Okay, so what is quantum parallelism? Now, in the classical picture, if you have 4 input to evaluate this function, and then you have to do this 4 times. But in quantum state, you can encode this 4 state using 2 qubit, because the 2 qubit allows you to represent the 0, 0 state, 0, 1 state, 1, 0 state, and 1, 1 state. And then through this quantum gate, then you can evaluate this state just in one operation. So you will get this in your you can do the calculation just in one step. So here we're using 2 operation, okay, and cook and this qubit. And then if you have n qubits, then you can do a 2n operation using n qubit. Now for the memory issues, classical memory use we have n numbers. Yeah, say if you have the large n, that is say the large n is equal to 4. So we have this 4 times 64 bit of memory. And for quantum memory, then you only have you can store 2 to the power n coefficient using n qubit. So the memory is only the logarithm of n. So it's much smaller than the linear proportionality. Now, there's a limitation about the quantum computing is, although we can do quantum, parallelism, but the bottleneck is at the measurement. say you can have four, you're doing this computation at once, and it will result in either one of it. But each one has the probability amplitude A, B, C, D. So you have to measure this. You have to measure this, but you only can measure, say, the F00 state with the A square because of the bond rule. So so if you repeat the measurement, say 4 times, it might still not see all the possible outcome, because maybe you only see A, B, C, because D has a small probability. So so there is you need to find a way to detect to measure the outcome. That is the one bottleneck for the quantum computation. So people also say quantum computer is not going to replace a classical computer. It's only good at solving a certain type of a problem, but not all of it. There's something called a hybrid approach, in which we combine both the classical computer and quantum computer together to achieve the task, achieve the purpose. Okay. Now, one of the phenomenon is not found in classical is in the quantum mechanics. You have something called a superposition of the state. There is using the direct bracket notation. You can represent the spin-up state and the spin-down state using this column vector. So in quantum mechanics, before any measurements, the state, the quantum state, has the two possibility, right? So you have to. This is the quantum state of your initial the status. It's not like in classical picture. You will observe, say something is in a definite spin up or definitely a spin down state, but in quantum mechanics, if you prepare something, if you have prepare your quantum state, in general, it is a superposition of a spin up and spin down. So this is something that you don't see in the classical picture. So you have to write, this is the so-called superposition principle. And then we have the coefficient. Here is 1 over square root 2. We call this the probability amplitude. One way to write this is alpha and beta. And the the magnitude square is equal to 100%. Now you might have more than one particle. So if you couple two particles, then you will have a state like this: 0 and 1, 0 and 1, 0 and 1, 0 and 1, and then this will be a 4-component column vector. So this is 0, 1, and denote that we have a 2 particle. And to form the multiple qubit, you have to use the tensor product. So this is the definition of the tensor product. Now for n qubit, then you will have the tensor product of 2 to the power n, a column vector with 2 to the power n elements. Now you can represent a spin up and spin down state using the block sphere. So for spin up, then we say is pointing in the North Pole, and for spin down is pointing down. And but in general, the quantum state is located on the surface of this sphere. This is called the block sphere, which is parameterized by the angle theta and phi. So in general, any single qubit state can be represented by this expression over here. And Mrs. Aninda, she's going to do a demo how to use Qiskit to make up this block sphere for you. So then she will do this, okay? But so in quantum computation, you just have to create quantum gates, and each gate can be represented by a matrix. And for a single qubit, then this is the matrix representation for the X gate, the Y gate, and Z gate, and so on. Now, all the quantum gates are unitary. That means their complex conjugate transpose is equal to the inverse. Quantum gates are reversible. That means you can, from the output, there is a one-to-one correspondence between input and output state. But it is not the case for classical gates. Now, it's like in classical computing, we define a set of a universal set of gates. That means you can express any gate in terms of a universal set of gates. Now, if you have a quantum state going through a quantum circuit, so the way we write this is because we read it from left to right. So we see the Y gate first and then the X gate. So if you write this in terms of matrix, then we have X, the Y operate on this quantum state first and then the X gate. So this is the way how we, in the picture, it is the Y coming first and then X, but when you write it out, then we have X and Y. Okay. Yeah. So here is the matrix representation of the single qubit gate. This is very often you will see the Pauli matrix XYZ and the Hadamard gate, and also the phase gate and the S and T. Those are the phase gates. So I don't have time to go through this, but you definitely will learn this from books on the quantum computing. That is about this is the matrix representation for the single qubit. Another very often quantum state is the so-called plus state, which is defined as the 0 plus 1 state, and the minus state is the 0 minus 1, which is the superposition of the spin up and the spin down. The only difference is there is a phase difference here. Okay, now the letter operator is about people they use it in the quantum chemistry calculation, but we will not use it in this lecture. But this is only for your reference. Okay, so this is how you take. Let's say if you take the tensor product of 1 0 0, So this is the way how you construct the 0, 0 state. Now also people use the decimal representation. Say if we have 1, 0, okay, so this is the 1 state, this is the 0 state, and this is your 4 column vector with a 4 column. This is the 1, 0. And you can also name this 2 state because it's like a binary string. Okay, 1, 0. So these are all the 2-qubit state, right? So this is the 0 decimal, 1 decimal, 2 decimal, 3 decimal. And the control knot, I'm sorry, I didn't have a picture over here. So what the control knot did I have it in here back? Oh, anyway, sorry, I forget that. What I mean is it's a gate for a 2 qubit. Let me see if I have something. So think about this, okay? Yeah, the control. This is the control U. This is the control knot is also like the control U. Okay. Because I don't have the control knot gate, so let me what it does is if we have the first qubit in the 1 state, then you will change. If the first qubit is in the 0 state, then you will keep this second qubit the same. It does not change. But if you have the first qubit is in the 1 state, okay, like here, okay. I think I shouldn't have this. If it is the first qubit is in this spin down state, then A, B, this is 1, 0, 1, 1. This is 1, wait. This is the one state. I'm doing something not quite correct. This is okay. I'm using the control U state. Okay, so we have the control bit on the top and the target bit on the bottom. So for the control U gate, if the first bit is 0, then you don't apply anything on the second bit. But if you have the first bit on the 1 state, then you will apply the U gate on the second qubit. Okay, say the U0 and the U1. The U's. Okay, and this is the control U gate doing. Now this is the general form of the U gate. You can write in this way or this way. And by going through this operation, then you can see the matrix equivalent of the control U gate is like this, A, C, B, D. So if we have the Z gate, remember, the Z gate is 1 minus 1 in the diagonal. So this is the matrix for the control Z gate. This is the matrix for the control rotation Z gate. So this is a general form of the control circuit. This is the case for the 3-qubit case, A and B. So if AB is a 0, then you don't do anything unless A and B is stay at the 1-1 state. Then you switch this qubit C from 0 to 1. And 1-1, then you switch the 1 to 0. You can also model the quantum gate using the classical logic gate. So here, this is a picture. On the left is the classical, and the right is the quantum gate. So you can. So this is what we do in the simulator. Is you try to simulate your quantum circuit using a classical circuit. So people are doing this. Of course, we have very limited number of quantum bit. So we for academic research, we use a simulator for the quantum circuit. So we can, if you have more CPU or GPU power, then you can simulate hundreds or thousands of qubits. So if you have a quantum circuit with multiple qubits, then what you have to do is you just have to follow the quantum state. Say what happened on the left, and then apply, say here's the Hadama, 2 Hadama. So we have this part is you have to form the tensor product of the 2 Hadama gate, and then operate that on to your initial state. And then you go through this control NOT gate, okay? So, and then you have another Hadama. So this is what you're doing. So this is the tensor product of this Hadama. And then we have the control X in the middle. And at last, we have the Hadama again. So this is the matrix representation of this circuit. So you just have to follow this step by step, and then you will find the outcome here. So the idea is you have to design a circuit so that, say, let's say you want to search for something, a search problem. So you just have to design your circuit in such a way that the solution will single out with a very large probability. Now, as I said, here you only have the probability amplitude. So that means you single out the solution. And then by the time you measure, then the solution will have the highest probability. But sometimes you might see the other solution. Not other solution, the wrong answer. Okay, but it's really very small probability. So this is the idea of quantum computing. You want to single out your solution with a high probability amplitude. So here's the universal set of gates for the classical, like the NOR gate, NAND gate, and so on. And you also have something similar like this in the quantum, like the rotation X, rotation Y, rotation C, and the phase shift gate and the C0 gate. You can also verify this is not the only universal set. You might have other universal set. Now, there's a theorem called the Solovit-Kati theorem. They say you can approximate any single qubit gate by the order of log K1 over error gates. if you want to approximate something with a small error, it goes by 1 over the error, but it goes by the log of k. That is, you can approximate something according to this expression. But k is something in between 1 and 2. But is it between 1 and 2? This is an open question. But the thing is, you can approximate any single gate with other sets of a universal set of gate. This has to do with the engineering problem. So maybe some of the gate is more coherence time. They are more stable, or it may be easy to make. So that is why people want to do this. So measurement base is, as I said, you have to do measurement eventually. So sometimes it's more easy to do the measurement in the spin up and spin down direction. And sometimes you may want to use the plus or minus state, right? Because the time limit, I don't want to go for all the details in here, but keep in mind, you can do any measurement just by choosing a different basis to fit your purpose. So let me see. I have. Okay, now this is. Let me see. Okay, maybe. So let me. Okay. So let's say we have some initial measurement. Okay, and then we have a measurement operator AK. So the probability of measuring the eigenvalue of AK, this K is associated with the small AK, is to compute this matrix elements. And then after the measurement, the state, which is a linear superposition of all the A of K. But after measurement, it only collapses in one of the eigenstate. So after the measurement, this is the final state, which in the denominator you have to do some normalization. So now for the measurement, spin up, spin down state, this A, we have the A spin up and the A spin down using this representation. And if your state start from A0 and A1, a linear superposition of the spin up and spin down state, then after measurement, then you will get this. Okay, you have a normalization for the this factor, A0 divided by the absolute value, the magnitude of A0. So when you square this, then this you have 100% at spin up. So that means after the measurement, the state collapse to one of the spin state. So here is if you apply this A0 measurement, it collapses to the spin up state. There's also something called the no cloning theorem. That means you are not allowed to copy the quantum state. Sorry. there's a this is the proof. Okay, the proof is proved by contradiction. Okay, so let me just highlight the procedure and then left the rest for you to read. There is suppose we have a state which is a linear superposition of 0 and 1. This is the plus state. Now, if you want to copy this, then that means a unitary operator exists. Then we have a copy. This the plus and plus. Now, if you put it back, then the plus and put it back, then you will get something like this. Now, if the unitary gate also exists, then when you apply the U gate on A0, B1, then you will also copy this 0 to 0 and 1 to 1. But then these two operation also are possible, but you need these two equal. And you see, if you require this and this equal, then you will see either A or B is 0. So it is not allowed. So but in some special case, you can possible to copy. It's like you can copy both 0 and 1. Say like the C0 gates. So when you apply the C0 gate on 1, 0, then you will result in 1, 1. If you apply this as 0, 0, then you get back 0, 0. So you can copy orthogonal state. Is possible, but in general, it is not allowed. But there's a special case. Those are the state. If the state are orthogonal, then this is possible. And then let me get to the entanglement. Entanglement is a phenomenon in quantum mechanics that is you have you pair a single object with the total spin equal to 0, but then through some physical mechanism is you have a child particle, okay, sending in opposite direction. And this two particle could, before you do any measurement, it could be in the spin up and spin down state. But when, let's say this is Alex, when she measure, okay, this quantum state, assuming she measures spin up, then if this two particles are entangled, then it's definitely Bob will measure spin down. Regardless how far it is the distance between Alex and Bob. So this kind of a phenomenon that seems strange, right? In classical, that means by measuring, say Alex doing the measurement, then the effect seems instantaneously fast and have an effect on Bob. So this is a phenomenon only happen in the in quantum mechanics. This has been experimentally verified. So that means there is certain level of correlation between this two particles. And in fact, this has been verified since 1972 and through several experiments. And the recent experiment has shown that this entanglement action can propagate at least this is 100. This is 10,000 times faster. But there is no information transmitted. This does not violate Einstein's special theory of relativity. Okay. Now, because we still have Aninda to give the demonstration, so I have to reserve some time for her demo, and then I will skip this entanglement part. Okay, and also about this is the entanglement belt state. By entanglement, that means you cannot decompose your state into the tensor product of two states. This is what we mean by the entanglement. You can prepare a quantum circuit for certain a quantum state. So here at this entanglement state, you can build a quantum circuit which compose with starting with spin up first spin up state, and then with the xk on the second qubit, and after that then the Hadama on the first qubit, and then take the control knot after that. So if you follow the quantum state, say this is 0, 0 state, and then the second qubit undergo the x2 qubit, x2 gate, which should flip the second qubit from 0 to 1. And then so this 1, 2, 3, 4 is this 1, 2, 3, 4. So what you're doing is you follow this calculation. Then at the stage number 4, then you will get this final result, which is this psi plus state. Okay, all right. So that's all I have to talk about the entanglement. I think I don't have time to go through the Deutsch algorithm. I think I would rather keep it for my part 2 lecture. That's okay, because this is a ongoing lecture. So I will go through this sometime later, and also about the hardware technology, and we see a lot of people using different hardware technology for try to build a quantum computer based on different hardware. But at the moment, we don't know which one is a better hardware. This is still an ongoing. Yeah, a lot of work is going on. So we don't know which one is better at the moment. But companies are spending a lot of effort and money on doing that. It's all because of the difficulty is all because of the qubit is very fractal. Okay, it can be easier to flip from a spin up to the spin down state. So so there's there's a lot of work on the quantum error correction, and people try to build a quantum circuit with they correct the error. And fault tolerance is something, as long as you can keep the error below some number, then you can perform reliable quantum computation. So you have to make your error correction as good as possible. And if you can keep the error below some number, then you can do a reliable computation. So hope that I will have the opportunity to give this lecture later as well. I'm still learning, but okay. Now people they have opinions. Some have a strong opinion about the possibility of quantum computation. So there are pros and cons, and say the pros is say people publishing a paper. They say they cannot have close to the fault tolerant memory. But another cons is people say they make use of the tensor network classical computing. They can outperform the quantum computing. And the recent development is people come up a even more efficient algorithm for prime factorization. So this is by a fellow from New York University, Rick Giff. It come up a even more efficient quantum circuit rather than the Shor. Okay, so this is the improvement. And also a recent, just this month, March 1st, there's a article, not peer-reviewed yet. They say there's a computational supremacy in the quantum simulation using a D-wave. But as I say, D-wave is not a universal quantum computer. So you see, there's a lot of there's a pros and cons. So in March 9th, Google launched a 5 million prize to find the actual use of quantum computer. It's because so far we still don't know whether the quantum computing has any a commercial practical usage at the moment. So people are pushing this very hard. And as you see in the past, at the beginning of the classical computer, this is how it looks 50 or 60 years ago. It's a huge and a large. It can only perform 5,000 flops. So, and when you see back how it moved from 1950 to 2010, then you see the speed moving from 0.01 megaflop to now. Okay, so there's a huge difference. So my opinion is there is no theory to prove that the quantum error correction is not possible, and there's no theory to say it is fundamentally unfeasible. And I think scientists is ambitious to control the microscopic world, will not stop. So, and we also see the AI winter. Okay, we know AI is booming now, but years ago, we see AI is kind of stop making any progression, but now we see is booming. And also, people are also looking for high temperature superconductor. It's not achieved yet, but the scientists are not giving up. So I am cautiously optimistic If it is succeed, then it is good. If not, then I think we will have a deeper understanding of the quantum world. And I believe we won't have a situation where we all lose. It will be a win-win situation, even though we will gain a more deeper understanding of the quantum world, even though we were not able to achieve the ultimate goal. I think that will be useful in other quantum technology. Okay, then thank you for your attention. And before I switch to Aninda, we still have time for a couple questions. And I like to see if anyone like to pose any question. I try my best to answer. Yes. Yeah, I may be going a little bit fast, but I hope that it will give you a flavor. If for people who are beginner, I hope that will give you an overall idea about the quantum computing. It takes yes some time to understand the material. Okay, now if okay, let me ask one more time and see if people have question. So if not, then let me pass my microphone to Aninda. So Aninda, can you share your desktop?
Yes, Prof.
Okay. So let me see setting. I think you should be able to share.
Eh?
I think I see your screen. Did you?
Professor can see my screen?
Oh, yes. Okay. Yes. Good. Okay. Go ahead. Yeah. Use full screen mode.
Yeah.
Yeah. I can see your face now.
Yeah. So I will start now, Professor.
I didn't see yours. Okay. Yes. Okay.
Yes.
Okay. Okay. You might. Yeah. Full screen mode. Okay. Okay.
Yeah.
Okay. I'll close my microphone.
Yeah. Hello, everyone. Today I would like to present about demo Qiskit by using IBMQ. So today presentation, I will introduce the IBMQ platform and then mathematics behind quantum computing, basic quantum circuit, quantum computing measurement, qubit states, single qubit, and multiple qubit, also entanglement state. The first, before we do quantum computing, we have to use the platform or we use the local software, for example, Anaconda or Python, to run the quantum computing code. This is IBMQ is provided by IBM company to do quantum computing simulation. So before we use the platform, we have to create the account. If we in the previous, we see, if we open the IBMQ website, and then we can see the sign-in. So we can create a new IBM ID, and then we fill our information or account information, and then we will get the code verification from our email. After that, after we've verified the code, we can use the IBM Cube platform to do quantum computing. So how IBM Cube platform look like is like this. In the tab bar, we have the dashboard, and then computer resources, and also the information about our jobs. And in another side, we have the account information. Also, we can see the documentation about the Qiskit, how we create the code in the by using the IBM Q. And in IBM, they also provide the course for learning. They have also IBM Lab that we can run our Python code. In this part, we can see, and then we can click, and we can learn more about the IBM Qiskit. Also, in IBM, we have to know about IP token. This will provide in our account information. So IP token will use when we use the local environment. For example, when we do the quantum computing by using Anaconda, we install Anaconda in our local computer. So we have to log in to the IBM Qiskit by using API token. This is how IBM Q dashboard looks like. In here, we have information about system name, IBM Brisbane, IBM Osaka, IBM Kyoto. This is the system name. And then how many qubit that we can use, how maximal qubit that we can use. And also information about the APLG. This is error per layer gate in the chain of 100 qubit. And also information about the clocks circuit layer operation per second. This is the how quantum processing unit execute per unit time. Also, when we doing the quantum computing, we have to know the back-end simulator, what kind simulator that we use. In here, we can use simulator stabilizer, simulator MPS, and others. For example, test vector, this is also we can use, and we can have the information how many qubit that they provide, or that we can use to run our qubit. This is the maximal qubit for each simulator. So IBM Q jobs, in this tab, we can know what kind of jobs that we run in the backend. We can check it by using the status. This is by using the Python code. We also can use the Google Colabs to run the IBM Q Qiskit. The mathematics behind quantum computing. This is metric operation. How we do metric operation by using Python. For example, in here we have by using the package NumPy, we can do operations subtract, multiply, dot, or divide, or matrix transpose, and this is the result of the calculation. In quantum computing, we also do the tensor operation. This is the simple operation, for example, for sum, and then subtraction, and then tensor product, also for dot product. And this is the result of the calculation. Basic quantum circuit. We build quantum circuit by using the Qiskit. This is the package by IBM. So quantum circuit is the collection of the qubit and a least interaction that acts on this qubit. For example, when we want to create a new circuit with 2 qubits. So in here we use the common quantum circuit. This is 2 means we will create 2 qubit. So if we want to create more than 2, for example 3 or 4, we have to change this parameter. And this is the result how our qubit looks like. This is Q0. This is the index start from 0. So Q0 and Q1. This is the information inside our qubit. For example, 0 and 1. This is the qubit 0 and this is qubit 1. And this is 2 means the 2 qubit. And Q is the name of the quantum register. So, and then we can add the gate to a qubit. For example, we add the X gate to qubit 1. Qubit 1 means we use the index 0. So in here Q0, we add by using QC dot. This is, we can change depend on our definition. In here for quantum circuit, and then X means X gate. 0 means we put the X to the qubit 0. And then when we want to create the other gates, we can use, for example, Y and Z. So we just put the Y after we quantum circuit the definition, and then Y and Z, and then this is also which qubit that we want to add, 0 or 1. Quantum computing measurement. The function measurement all, this is method that used to extract the output in quantum circuit. We can also use for each qubit to do measurement. Each measurement tells us a specific qubit to give a specific output bit, 1 or 0 or other. So this is the example. We create the 4 quantum circuit and add its measurement for each qubit. For example, this is 4 qubit 0, 1, 2, 3. And then for all we put the measurement, this one. This is measurement 0, 1, 2, and 3. We can use this command. And then to look up how about our measurement, we can call the quantum simulator. This is how we call the simulator. For example, we use the air simulator. And then first we have to call the package from the Qiskit air, and then air, we can change the number, we can change the name of our definition in here. So, and then get backend, we use simulator, and then this is, we want to run our simulator and give the job to simulator. And in here we get the result for our measurement. The output 0, 0, 0 in here means we give measurement for qubit 0 until qubit 3. So this is 0, 0, 0 because we doesn't put any tags to our qubit. In here we see 1024. This is the fourth number of short. Short means how many times to run the circuit. This is the example for measurement. For example, we want to put X gate. We add NOT gate in qubit. In here, I want to put the in qubit 3. So in here we give definition X3 means we want to put the NOT gate or X gate to qubit 3. And we can see how our measurement looks like. In here, the output changes from 0 in qubit 3 into 1. So in the X gate, we flip 0 to 1. This is another example. For example, we want to put the X gate to qubit 0. So we put in here. And we call the measurement. We get 1, 0, 0. Because in here we just have 3 qubits. 2 in here means the 2 classical bit and represented in here. C2 means 2 classical bit. And then how about if we want to put the control node or C node gates measurement? We can put in here Cx. We call the function Cx. And then we put the control node from key 0 to key 1. Key 0 means control qubit, and then key 1 is target qubit. So we test the control node or C node gate, and then we build 3 qubit in the 0 state and 2 classical bit in the 0 state. In here, 3 qubit, and then use 2 classical bit and add the X, gate X into key 0. And we put the C node gate from qubit 0 to qubit 2. This is 0 and then this is qubit 2. And we check the measurement. So X is the encode input. This is the C node gate. We do operation on the bit to flip the bit, and then we extract the output. So this is the result without C node. We see in here 1, 0, 0. This is come from here. And then without C node, with C node, we flip the result to 1. As professor before explained that we just key 0 will flip the state of Q2 if and only if key 0 in the state of 1. This is 1. So change the 0 to 1. Qubit state. In quantum circuit, qubit always start from the 0 state. For example, when we first time to draw the qubit, for example, in here, Q, always start from the 0 state. This means the output is 0. And then how if we want to transform qubit 1 into state 1? We can use, for example, in here, I give the definition initial state 0 flip to 1. This is the output before we change, and then this is after we change to 1. So use Qiskit simulator to view our result. In here is the same with the previous and then measure our qubit to see the result. This is we put the measurement to see our result. And we can see that from 0 to 1. Transform qubit into another state. How if we want to put qubit not in the 0 or in the 1, but we want to put in another state. We just use definition in here, and then, for example, in here we want to put in the superposition state. We give definition in here, and then the result, we do the measurement and we call the simulator. We see the result. This is 0, 1, and then in here 0.5 and 0.5. This result means we have 50% in the 0 state and 50% in the 1 state. This is called superposition. So how qubit state Blossberg representation? For example, in here we have the qubit in the 0 state. This is how the Blossbergs look like. We can call the step vector function to do plotting our Blossberg. And then this is the plot of qubit in the 1 state. For example, in here we add the X gate, and then our Blossberg looks like this. This is, we call it spin done in the 1 state. And then plot a qubit in the superposition state. For example, we use the Hadamard gate, and we add our 2 qubit, and then this is the result of how the Blossberg representation. This is called superposition, not in the 1 or either in the 0, but in the superposition state. So how to plot the qubit in another position state? We can put parameter in here. This is the theta, pi, and then radius. And then, for example, in here we after we put the equation, our Blossberg looks like this. In the between 1 and the superposition. Single qubit gates. This is how single qubit bit gates representation in the matrix. And then how we build the single qubit gates. This is for example, looks like previous before. We build the X gate. So this is how X gate looks like by using the Blossberg representation. The result is the 1. Multi-qubit state and entanglement. In here we want to create 2 qubit and apply Hadamard gate for each qubit. For example, in here we create 2 circuit with the 2 Hadamard gates, and then we check the result of possible of 2 qubit state. This is the step vector, means the position in our state. This is 1, 2, 3, 4 because we have 2 input. So 1 qubit will give the two output. And then we create 3 qubit and apply Hadamard gate, for example, in here, how our results look like. We get 1, 2, 3, 4, 5, 6, 7, 8, the result or our state position. So a single bit has two possible state, 0 and 1. One qubit have possible output 0 and 1. So if we have two bit, this is have 4 possible state, 0, 0, 0, 1, 1, 0, and 1, 1. So in here we have 4. So if we have n bits, we will have two square n possible state. Multi-qubit gates, this is we want to create to circuit and apply Hadamard gates in key 0. This is the result. So this is our amplitude. It produces amplitude. For example, in here when we create the two Hadamard, one Hadamard and then Q1. So this is how our amplitudes look like. And then we apply CNOT gate to do entanglement. Entanglement means we put our two qubit become one. So for example, in here we want to entangle Q0 and Q1 by using the CNOT gate. So this is the output after we do entanglement. After we do measurement, we can plot the result of our entanglement. For example, in here, because we use Hadamard gate means we put in the superposition. So this is the result 0.5 and 0.5. So when we check the entanglement of 2 qubit, in here we cannot see where our state or how our state looks like. This state cannot be written as 2 square qubit state. It means that we lost information when we try to plot our state on 2 different qubit. So this is before we do entanglement, we have qubit 0 and we apply Hadamard gate. This is how our qubit looks like. And then for Q1, we doesn't do anything, and then we entangle these 2 qubits together, become 1. So this is how our Bloch-Spear looks like after do entanglement. So the number of 0 in the state of proportion to the state in the x-axis. In here, how Bloch-Spear representation. This is the 0 state. So in here we can also see the amplitude for 0 in the top and then 1 in the bottom pole. This is, we call it entanglement when 2 qubits become 1. This is all of my demonstration about Qiskit. Thank you.
Okay. Yes, thank you, Aninda. Okay. Can you hear me?
Yes, Prof.
Okay. Yes. We have time for 1 or 2 questions for Aninda. Okay, so if there's no more question, then we can close today's lecture. Okay. And thank you very much for all of you joining us. So I look forward to see you next Friday. Okay, I will keep you posted, inform you. I expect the next talk is same time. Okay, Friday, next Friday, 2 p.m. at Taiwan. And then we will have people from Indonesia and talk about classical machine learning and deep learning. Okay, I see you guys soon. Okay, bye-bye.
Thank you, Prof.
Thank you, Prof.
Bye.
Thank you,
Thank you,
Prof.
Aninda.
Yeah, bye.
Bye.
Thank you, Prof.